Imagine you're piloting a tiny ship, and suddenly space ahead turns into a chaotic maze of spinning rocks, no music, no warning. Just you and a dense field of irregular asteroids ready to test your reflexes. If you stay until the end, you'll know what these strange asteroids are made of, how they move, why they matter for Earth, and how a future mission might surf through them without getting smashed. Picture this. You're watching a calm, starry sky. Then you zoom in. The empty space between planets isn't empty at all. It's crowded with rocky leftovers from the birth of our solar system, quietly orbiting the sun. Some look like peanuts, others like potatoes or broken sculptures. Each spin is clumsy and uneven because their mass isn't spread out smoothly. They wobble like badly balanced spinning tops in the middle of black space. Now, why are they packed into dense fields? Gravity. Over billions of years, these rocks settled into stable zones, like the main asteroid belt between Mars and Jupiter, where their orbits don't easily cross big planets. But dense in space is different from a movie scene. Even in a crowded field, there's still huge distances between most rocks. You could fly for hours and not hit anything, unless you're unlucky or careless. Still, in the tightest regions, some asteroids pass relatively close. Their gravity tugs on one another, slightly changing paths over time, like slow-motion billiards across millions of years instead of seconds. What are they made of? Many are mostly rock and metal. Some are rich in iron and nickel. Others are darker, full of carbon and complex molecules. A few are icy, like dirty snowballs hiding in the cold outer regions. Imagine slicing one open. You'd see a chaotic mix, boulders, dust, maybe pockets of metal. Some asteroids are like rubble piles, just loose pieces gently held together by their tiny gravity, ready to crumble if disturbed. So how do these dense fields form? Collisions. Over eons, larger bodies smash into each other, breaking into families of fragments that continue to share similar orbits, filling certain lanes with more debris. Each collision shatters, melts, and reshapes material. Some pieces spin off into wild paths, others settle into the dense regions we study today. It's like a slow, endless recycling system made of stone and metal. You might wonder, is it really dangerous for spacecraft? Yes and no. Space agencies carefully plan safe routes, but even tiny grains can damage instruments. That's why we use shields and smart navigation. To navigate, we map asteroid positions and paths with high precision. Then we choose trajectories that thread the gaps. In a dense field, timing is everything. You arrive where a rock isn't, not where it is. Now, why should you care about these irregular rocks from your couch on Earth? Because they're time capsules. Many haven't changed much since the solar system formed, storing clues about our cosmic origin. By studying them, we learn how planets like Earth came together, what ingredients were present, how common are metals, water, and carbon. These questions help us understand not just our past, but our possible futures. Some dense fields may even be treasure troves of resources. Metals for building in space, water for fuel and life support. Instead of launching everything from Earth, we could mine the sky one day. And yes, a few asteroids can cross Earth's path. A dense region of debris tells us where past collisions happened and where future fragments might come from, helping us predict and avoid potential impacts. Scientists track these objects with telescopes and radar, building catalogs of their orbits. When we know where they are and how they move, we can design missions, or if needed, gentle deflection strategies. Back in our dense field, look how chaotic it seems. Yet it's not random. Every orbit follows the rules of gravity. Once you understand those rules, the chaos turns into a predictable, beautiful cosmic dance. Each irreg shape also tells a story. Sharp edges, maybe a recent break, rounded contours, many tiny impacts over ages. Surface color differences, clues about ice, metal, or carbon hiding just beneath. Imagine future explorers steering through such a field, hopping from rock to rock. One asteroid could provide fuel, another metals, another scientific data, a whole toolbox orbiting the sun, waiting to be used. But first, we need to know these places like our own neighborhood. That's why missions fly close, map surfaces, and sometimes bring back samples. Each visit turns blurry rocks into well-known worlds. Standing on one of these asteroids, if you could, it would feel strange. gravity so weak you could jump into space with a single push. The horizon would curve sharply and the sky would be filled with other wandering rocks. From that tiny world, the dense field would look like a slow storm of stone around you. No sound, just endless motion. Every spin and drift silently rewriting the shape of this scattered mini-solar system. As we keep exploring, we'll map more of these dense regions, testing new ways to travel, protect ships, and maybe use asteroid materials. Each discovery makes the solar system feel a little smaller, a bit more reachable. So next time you hear asteroid field, don't think only of danger. Think of ancient archives and future fuel stations, all hiding in those irregular, lumpy rocks drifting between the planets. You've just flown through a dense field of irregular asteroids and learned what they are, how they form, and why they matter. If you want to explore more strange corners of space, you already know what to do.